Alright, everybody. So just wanted to take a quick moment and first go over those last few problems. So this is where I left you off, and I want you to understand with these problems, it's really straightforward. We have our formulas, we use our formulas, and we simplify using the unit circle. So if we're talking about 3 pi over 2, that's the same thing as 270. So really we're talking about cos of 270 plus theta. Right, we have the cos addition formula, so we write the whole thing out, and we simplify what we can simplify. Now, not every problem is as straightforward like problem 4. So problem 4, this only happens with tan at 270 and 90. Tan at 270 is undefined, tan at 90 is undefined, so we can't use the tan formula. But tan can always be separated into sine and cos. So even though comparing problem 4 to problem 3, there's more going on, it's really just doing problem 3 twice. So we got the sine subtraction up top, we have the cos subtraction on the bottom, simplify and get our cotan. Right, jumping over to 5, 6, and 7 and so on. So the scenario here is that we're given a ratio. We're given sine is 12 over 13, which means y is 12, r is 13, and with Pythagorean theorem, x is 5. For beta, right, we have x is 3, r is 5, Pythagorean theorem to get y is 4. And then again, we have all the information we need, so we use our formula. It's a very formula-driven unit. It's not, I don't think this is one of the hardest things we're going to do. We set it up, we simplify, and we go from there. All right, so here, using the exact same numbers over and over and over again, cos addition, cos subtraction, sine addition, sine subtraction. On the back, getting a little bit trickier with tan. Right? So with tan, right, we have the same numbers as before, but we have our different formula. One of the key things we have to work on with the tan formula is common denominator for everything so that we can drop the denominators and simplify. So in this scenario, the common denominator for the entire problem was 15. So 12 over 5 became 36 over 15. 4 over 3 became 20 over 15. 1 became 15 over 15. And by doing that, it just made it algebraically easier for us to drop the 15s and solve. Right? Similar problem for 9, but since it's tan addition, we have a plus in the numerator and a minus in the denominator. Right? And do that, we get 56 over negative 33. Last problem on this worksheet, another identity, a basic identity. Right? So we have the 360. Right? We do cos subtraction formula, we simplify and get cos x. All right, time to do our new idea. So our new idea is that. So what we've already established is that if we have sine addition is sine A cos B plus sine B cos A. Right? Cos addition is cos A cos B minus sine A sine B, and tan, we got this fraction idea, tan A plus tan B over 1 minus tan A tan B. So what we're looking at today is what happens if we have the exact same angle. So imagine the problem was like sine of 90. Now I'd never ask you to use this formula for sine of 90 because we would use 45 plus 45, but sine of 90, we don't need this formula. We know sine of 90. On our unit circle, we got 0, 1, sine of 90 is 1. But the idea is that if we were using this formula, we would break it up into 45 and 45. But for the purpose of what we're doing, never use this formula for sine 90. Sine 90, unit circle problem, done. So creating the formulas here. So if I take the above, and I, instead of beta, have alpha, I have sine A cos A plus sine A cos A. And if I simplify that, since they're exactly the same, I have 2 sine A cos A. So my double angle formula for sine is 2 sine A cos A. And the way we properly write this is equals sine of 2A. All right, now looking at double angle for cos. So we'd have, oops, not that, make an S. We'd have cos A minus sine A, which gives us cos squared A minus sine squared A. All right, awesome. There's our double angle for cos. So cos of 2 alpha equals that. Now, there is a variation here. So what we know from a previous unit is that cos squared x plus sine squared x equals 1. And we can use that to help us derive variations of this formula. So if I wanted to, I could write this as sine squared x, 1 minus sine squared x minus sine squared x. So I could sub in 1 minus sine squared x for cos squared x. By doing that, I get the variation 1 minus 2 sine squared x. So this is a second setup for our formula. Well, know what? I can go with another setup. Cos squared x plus 1 minus sine squared x. Oops, that's not what I wanted. 1 minus cos squared x. I messed up the formulas here. Minus cos squared x. If I distribute the negative 1, I have plus, so I'd have 2 cos squared x minus 1. Right, so in this scenario here, cos double angle has 3 different setups. And it doesn't matter which way you do it. There's different scenarios where it's going to benefit you to do it one way. There's different scenarios where it's going to benefit you to do it the other way. The last formula, so tan alpha plus tan alpha over 1 minus tan A, that'd be 2 tan A over 1 minus tan squared A. And that would equal tan of 2 alpha. So these are our formulas. And to be honest, these are not the most used formulas. Because if we think about what we have, if we're looking at unit circle, 30 plus 30 is 60, and that's on the unit circle. 45 plus 40 is 90, that's on the unit circle. 60 plus 60 is 120, that's on the unit circle. So most of the stuff that we would double is something that we wouldn't need this formula for anyway. Alright, so does this actually work? Now, I just want to show you. Alright, so if we think about a unit circle, sine of 60 is rad 3 over 2. Cos of 60 is 1/2. Tan of 60 is rad 3. So I don't ever want you to use this formula for this setup. But for the purpose of what we're doing right now, I just want to show you that it does work. So the key idea is that this is 30 plus 30, or 2 times 30. So when we do the work for this formula, we're using 30 degrees. 2 sine 30 cos 30, which is 2 sine of 30 degrees is 1/2. Cos 30 is rad 3 over 2. 2 times 1/2 is 1. This equals rad 3 over 2. So it does work there. So again, if we're looking at cos 60, we really have cos of 2 times 30. And here we have the option. It doesn't matter which formula we use. So if I went with the cos squared, cos squared of 30 minus sine squared of 30. So cos of 30, I got rad 3 over 2 squared minus 1/2 squared. 3 over 4 minus 1 over 4. 2 over 4 equals 1/2. And it works. And it doesn't matter which trig setup we use for cos double angle, it's going to work no matter what. Alright, tan. So again, we got tan of 2 times 30, which gives us 2 tan 30 over 1 minus tan squared 30. So tan 30 is rad 3 over 3, 1 minus rad 3 over 3 squared. Alright, so I got 2 rad 3 over 3, 1 minus, what do I got in this case? 1/3. Let me scroll down and get some space. So this would give me 2 rad 3 over 3 over 1 minus 1/3 is 2/3. Alright, algebra 2 rule, they both have denominator of 3. Cancel that. 2 rad 3 over 2. Cancel the 2's, which gives us rad 3. Alright, so again, never use these formulas for sine 60, cos 60, tan 60. I just want to present the idea to you to show you that you can use them. So when are we really going to use these scenarios? With something like this. This is what we're really working towards. So if I'm talking about cos, I know that my x is 5 and my x is rad 5 and my r is 5. So I got rad 5 squared plus y squared equals 5 squared. 5 plus y squared equals 25. Y equals rad 20. Y equals 2 rad 5. So for this problem, the key numbers, x is rad 5, y is 2 rad 5, and r is 5. And since we're in quadrant 1, everything is positive. Alright, so if we're looking for cos, in this scenario here, we have options. Cos, we have the 3 formulas. But know what? The fact that this is given to me, I'm going to go with the setup that this equals 2 cos squared x minus 1. Why am I going to do that? I know that's 100% correct. It was given to me. Right? They're not going to give me wrong information. If I use the y, right, if I mess up the y, then I'm going to mess up my answer here. Right, so if I go with this, I'd have 2 times, I'm not writing in highlighter, I'd have 2 times rad 5 over 5 squared minus 1. 2 times 5 over 25, which is 1/5 minus 1. 2/5 minus 1 is negative 3 over 5. Right, cos of 2 theta, negative 3 over 5. And the idea here is that, theta is an angle. If I were to do inverse cos negative 1 of rad 5 over 5, I would actually get, let me just see, inverse cos rad 5 divided by 5, I get 63.4 degrees. So really, what we're doing here is we're solving for 63.4 degrees. But what we do is cos of 2 times, in this case, 31.7 degrees. And that's what's going on here. But we don't need those angles. We cut those angles out of the scenario and just move forward. Okay. Sine. All right, so our sine formula equals 2 times, all right, so I got cos theta sine theta. So 2 times rad 5 over 5, right, that's my cos theta, while my sine theta is 2 rad 5 over 5. So I got 4 times 5 over 25, giving me 4 over 5. Last one, tan. All right, going with tan. So I got my formula. So I got 2 times tan is y over x. So in this situation, 2 rad 5 over rad 5, 1 minus 2 rad 5 over rad 5 squared. Well, what's great about this is that rad 5's cancel out in those individual fractions. So I got 2 times 2 over 1 minus 2 squared. 4 over negative 3. And that's my final answer there. All right. I know people are going to be disappointed in me, but I gotta bring this up anyway. Identities. And I promise, in these scenarios, these are not the most overly complicated identities that we're gonna have. I will give you all the formulas. This will not be the entire test. There'll be some of it, some basic stuff. But we'll survive here. Alright, so, similar rules in the past. We leave the left, we change the right. So you know what? I can rewrite this as 2 over sine 2 theta times sine theta over cos theta. Alright, so I move things around and brought the sine and cos. Well, know what? I got my new formula. So 2 over sine x cos x times sine x over cos x. Alright, so there is my formula. Alright, so that new formula becomes that. Alright, what can I do now? Cancel the sines, cancel the 2's. Alright, and I'm left with 1 over cos squared x, which if I bring it up is secant squared x. Alright, so the identities are here. They're not overly crazy, I promise. Alright, what do we got for this one? Well, for the purpose of my liking, I'm going to make it y plus x squared, which means I got y plus x times y plus x. Y squared plus xy plus xy plus x squared, which is y squared plus 2xy plus x squared. So if I bring things back in, sine squared x plus 2 cos x sine x plus cos squared x. Well, that's great because this is what I want to see. There's my double angle sine formula. Right, so in this situation here, this becomes the sine of 2x, which I need up there. Know what else is great? Sine squared x plus cos squared x. What does that equal? Equals 1. So there's our final answer. 1 plus sine double angle. Alright. Sine of 2x, we only got one option. There's our one option. Now, with the cos, we have 3 different choices. So this is what I got to think about. If I'm talking about cotan, cotan is cos x over sine x. So I'm going to need to have sine in my denominator. So if I'm thinking about which option I should go with, I'm going to go with this, because using this version of the cos double angle puts sine in my denominator. 2 sine x cos x, 1 minus 1 plus 2 sine squared x. Alright, so remember, key algebra idea, we distribute that negative. Right, this is something people make a little bit of an error with. Alright, so then we have 2 sine squared x. Alright, what can we do? We can cancel. Cancel the 2, cancel the sine. We're left with cos x over sine x, which is cotan x. Let's keep this rolling. 1 over 2 times 1 over sine x times 1 over cos x. If I combine them all together, 2 sine x cos x, there's what we want. There's one of our formulas. 1 over sine of 2x. If I bring this up, I get cosecant of 2x, which I want. Done. All right, what do we got here? All right, so if we look at this problem, extremely similar to what we were just doing. All right, we got 2 sine x cos x over 1 plus. Now, tan is sine over cos. So if I have my options for the cos double angle here, I'm going to go with the cos one because I want to make sure I have a cos in my denominator. 2 sine x cos x. I have my 1's cancel. I got 2 cos squared x. Cancel the 2's. Cancel the cos. I got sine x over cos x, which is tan x. Alright, given an honest assessment of where we're going, I would say 6 is a little tough. 6 is a little tough. 8's a little tough. So I'm not going to talk about those right now. After break, we can talk about those. The last one I'm going to do is right here. Alright, so I see sine. So I got 1 minus, and I got my cos of double angle. So since I see I have to end with sine, my best option here is to use the sine formula. So if I distribute the negative, I get 1 minus 1 plus 2 sine squared x, which gives me 1/2 times 2 sine squared x, which gives me sine squared x. Alright, I'm going to do 6 just because I'm sitting here and I might as well. Alright, so I got sine x plus 2 sine x cos x over 1 plus cos x plus what? So here we are in that predicament again. Well, I'm looking at this, and tan is sine over cos. And I'm thinking it may be beneficial for me down here to have everything be set up as cos. So 2 cos squared x minus 1. So I got sine x plus 2 sine x cos x over the 1's cancel, and I got cos x plus 2 cos squared x. Now there's not many options here. Well, know what I can do? This has a sine, this has a sine, this has a cos, this has a cos. So I can actually GCF out some stuff. So if I GCF a sine from the top, 1 plus 2 cos x. If I GCF it out a cos from the bottom, 1 plus 2 cos x. That works out nice because what can I do? Cancel all of that. And I'm left with sine x over cos x, which is tan x. Done.